Hi, I'm Quincy and this is my projectile motion physics lab. In this lab, I recorded the motion of an eraser in projectile motion and imported it into Tracker to track the position of the eraser at set time intervals. I then edited the starter GlowScript code to create two computational data sets, one that just accounted for gravity and one that accounted for gravity and drag. Then, I used this data and the data from Tracker to create a graph in Excel that compared these three sets to each other to see if the observed results were moving with ideal projectile motion. The purpose of this lab is to examine the effects of gravity and drag on an object in projectile motion. We did this by obtaining observed results and computing expected ones, and then comparing both of these on a graph to see how close the observed results were to the expected ones. Some important physics formulas are the velocity update and position update formulas that were derived from Newton's second law of motion. The velocity update formula is Vf equals Vi plus F net over m times delta t, and the final position formula is Rf equals Ri plus V average delta t. These formulas helped us determine new positions and velocities at a certain point in the object's trajectory. We also used a new formula for drag. Force of drag equals negative b v squared v hat, where b is the drag constant. We also used force of gravity equals negative mg. The system in this experiment was the eraser, and the surroundings were everything else that applied a force on the eraser, such as the air. The forces we considered were gravity and drag. Gravity acts in the downward y direction, and drag acts in the positive y direction and negative x direction. Drag opposes the motion, slowing down and reducing the range and height of the object. These were the only two forces that we considered in this experiment. We found that our model reached a lower max height and range than expected, and I will discuss possible sources of error later. Gravity acts in the downward direction, speeding up the downward velocity. Drag opposes motion in both directions, which shortens the range of the projectile and the max height it can reach. This is why the graph modeling drag and gravity is steeper and less tall than the graph modeling just gravity. We would expect our observed model to be more similar to the model with gravity and drag, as drag is an important force to consider, and this was true for the graphs that I calculated. Important initial conditions that were the same for GlowScript and Tracker were the mass, time steps, total time, and initial velocity. The mass was 0.04, delta t was 0.033, the total time was 1 second, and the initial velocity was 2.957, 4.130, 0. Here is the video of my Tracker analysis. Here is my GlowScript code. Important parts are the velocity and position update formulas in lines 49 and 50, and the initial conditions of mass in line 46 and delta t in line 54. The formulas for drag and gravity in lines 79 and 80 were also important to finding the net force and using that to update the velocity and position in lines 84 and 85. Series 1 is the expected motion considering gravity. Series 2 is the expected motion considering gravity and drag, and Series 3 is the observed motion. As you can see, Series 3 reaches a lower max height than expected, and it has a steeper trajectory. This could be due to not accounting for other forces besides gravity and air resistance and errors in calculating drag. However, the other two graphs show what we would expect, with the graph containing gravity and drag being less steep and reaching a lower range than the one only considering gravity. Possible sources of error could come from errors in calculating the drag constant b, errors in Tracker that comes from the video angles, or errors in the Tracker markings. Additionally, we only considered drag and gravity as forces, but there could be some unknown interactions of forces that were impacting the motion. Because the observed graph reached a lower height and range than expected, we can suggest that the drag constant may have been larger than we had calculated, or that there was some unknown force also acting on the object that was not accounted for. Do any of your models predict a terminal velocity? No. During projectiles, the object does not experience zero net force, so there is no terminal velocity. We should try an experiment with the object falling straight down in freefall motion for a certain period of time to obtain an object moving with terminal velocity. What if the object were initially thrown straight up? If the object were initially thrown straight up with the same initial speed as in the original experiment, the time to reach the ground would be shorter as there would be only a y component of direction. Projectiles have an x and y direction of velocity, so they have to cover a greater distance with the x distance of range, which means it will take more time to hit the ground. Thank you.